So we learned hypothesis testing and confidence intervals for one population parameter, but now we're going to learn to compare two through a difference. So previously we learned to create a confidence interval or a hypothesis test for one mean mu or one proportion p, but we often want to compare two parameters in more realistic settings. For instance, mean spending before and after an ad campaign, proportion of customers who buy dessert on the old menu design versus the new, etc. So let's start in with an example. An insurance company's procedure for settling claims under $10,000 for fire or water damage is to require two estimates for cleanup and repair before approving the work. They collect data on 10 claims and investigate whether there is a difference on average between the two contractors. So this is going to be called the dependent or paired sample setting. It's dependent or paired samples because there is an observation in the first column that's linked to an observation in the second column. Each one of them comes in like a pair. So claim 1 has two quotes on it. And obviously that claim is linking those quotes together. In general, if claim 1 has less damage, both the contractor's prices should be lower on average. So we call this the dependent sample setting when there's something linking those columns together. Now, these data come in pairs. Each claim has two data points. So that's what makes them dependent. In this situation, we can just subtract the observations and look at just the differences in the observations. This is the same as collapsing the data to a one sample problem on the differences. So notice that I've added a column to my data set. And you can download this data set. It's linked with your lecture notes. So please download the CSV file and follow along with R. So I've got the difference column now where I literally just told R to subtract column A minus column B. So notice 5,500 minus 600 equals negative 500. 1,000 minus 900 equals 100, etc. All right, so in the dependent sample setting, we're going to conduct a one sample t-test or t-interval on the differences. And the usual assumptions hold: the independence of observations and that the sample mean is normally distributed. And remember, there are two ways that we can get that the sample mean is normally distributed: either by D, the difference column being normally distributed itself, or by the central limit theorem as long as we have a large enough sample size. And we're going to use the usual test statistic for a hypothesis test, taking the sample mean minus the null hypothesized belief of the mean divided by S over the square root of n. That is a t-distribution with n minus 1 degrees of freedom, and the confidence interval is the same as we did before too. The sample mean plus or minus the t-critical point times S over the square root of n. So the math is the same as we learned before for inference for one mean mu. However, our interpretations are going to change. And fortunately, we can use R's built-in function that does the computations for us. So back to the example. Is there evidence at the 5% level to conclude a difference in contractor A and contractor B's bids on average? So what we want to use here is the t.test function. So I'm going to do a t.test on the difference column. And I'm showing you how I built the difference column here. I took contractor A's column minus contractor B's column to create those differences. And it gives us our hypothesis test output. Now notice this was a not equal to alternative hypothesis because we were just looking at whether there was a difference, not whether one was larger than the other. And so I didn't change the default about the alternative hypothesis. I got my test statistic, my degrees of freedom, and my p-value out right here for me. So we're going to use this to do our hypothesis test. So remember, step 1 is stating the alpha level. So the alpha level is going to be 0.05. Remember, if it's not stated in the blurb, assume it's 0.05. Step 2 is stating your hypotheses. So I've got a null hypothesis and an alternative hypothesis. So the null hypothesis here is going to be that the mean difference is equal to 0, and the alternative is that it's not equal to 0. But I like to know which way my stuff was subtracted so I can tell which one is larger. And so I'm going to write this as mu for contractor A minus mu for contractor B equals 0 for the null, and mu for contractor A minus mu for contractor B does not equal 0 for my alternative hypothesis. All right, step 3 is your test statistic, and I can see right from my output that it's negative 2.319. Step 4 is my p-value, and I can read it right from the output. It's 0.04556. Step 5 is comparing my p to my alpha. My p is 0.04556. My alpha is 0.05. That p is low, so the null is going to go. And I can make my conclusion. So notice that we reject the null hypothesis, and so that means there is significant evidence at the 5% level to conclude the alternative hypothesis. To conclude, contractor A and contractor B give different bids on average. Now notice that I'm adding the on average there because I didn't mention my parameter earlier in my little blurb. You have to talk about the parameter, and it's about the means. Okay, so that's our first hypothesis test on a difference with the dependent sample setting. So the math is collapsed down to a one sample problem, but we're going to interpret it as if it was from two populations. So now let's take a look at the confidence interval that was in that output. So the 95% confidence interval is negative 474.12 to negative 5.87, 0.88. So I'm going to first rewrite this with my parameter in between. So it's negative 474.12 less than mu A minus mu B, because that's the way I subtracted it. I took contractor A minus contractor B, less than negative 5.88. All right, now if you take mu A minus mu B and the only possible values for that are all negative, what does that tell you? That tells you think that mu B is larger. So I'm going to interpret my confidence interval that way. I'm going to say we are 95% confident that contractor B's bids are higher, and let's say that contractor B's average bids are higher than contractor A's by between $5.88 to $474.12. So as you can see, our interpretations changed just a little bit, but the math is still the same, and we're going to use R to calculate all of our numbers for us. All right, when the samples are not dependent, they are called independent. This is when you have two totally separate samples. There's nothing linking the observations in one sample to the observations in the other. So we've got our point estimate that we'll use. That's going to be the mean of sample 1 minus the mean of sample 2, and then the standard error of the point estimate. So the general case is going to be the sample variance for the first sample divided by the sample size for the first sample plus the sample variance for the second sample divided by the sample size for the second sample added together and square rooted. In the case that you think you know that the population variances are equal, then you can estimate that common variance by weighting the sample variance by the degrees of freedom available for each column in the following way. So you can take that pooled variance estimator in place of your S1 squared and your S2 squared in the standard error calculation, where that pooled variance estimator is that. And then, of course, you need your degrees of freedom. For the general case, it's going to be something called Welsh-Satterthwaite degrees of freedom. It's an approximation to degrees of freedom. Of course, this ugly-looking formula, you know you're not going to get a whole number out of there. And that's fine. R will do the calculations for us. And this is a highly approximate confidence interval. If normality does not hold, the central limit theorem still may apply, but the sample sizes must grow much larger. And then if you're assuming those equal population variances and using that pooled estimator, then your degrees of freedom are going to be very similar to what we had before. It's your sample size for the first group minus 1 plus your sample size for the second group minus 1, otherwise known as N1 plus N2 minus 2. And if normality of the sample mean holds for each sample and your variances are equal, then using this standard error with the pooled standard deviation yields an exact confidence interval. Okay, so again, we're going to let R calculate things for us. That was just a review from what you've learned in your last stats course. So we're going to jump right into an example. Zocor is a prescription medicine to lower cholesterol and is in the statin family of drugs. Prescription medication prices have been in the news a lot lately, and a consumer advocacy group wants to investigate differences. They get a random sample of Zocor prices from pharmacies in Colorado and Texas. Is there evidence at the 5% level to conclude the mean retail pharmacy price for Zocor is different for Colorado and Texas? All right, so notice that we have two totally separate samples. We've got some prices from Colorado and some prices from Texas. We didn't match pharmacies. We didn't do anything fancy. These are separate samples, so this is our independent samples setting. So I can still use the t.test function that we've already learned, but instead of just giving it one sample, I'm going to do comma a second sample. And then it will do the Welsh-Satterthwaite independent samples method for us. Now, in this semester, we're typically not going to assume that those population variances are equal. There's a way you can adjust your t.test function so that it will do that for you, but we're not going to cover the test for the variances being equal. And so we're going to kind of skip over that, and I just want you to know when you use that situation this semester. All right, so t.test with my two samples. This is the way that R is going to subtract them. It's going to be Colorado minus Texas because Colorado was first and Texas was second. It gives us our t-test output, and it also gives us our confidence interval output that we're used to seeing now. All right, so let's first interpret the t-test. So step 1 is stating your alpha level. Our alpha level is 0.05. Step 2 is stating the hypotheses. The null hypothesis is going to be that mu Colorado minus mu Texas equals 0. And the alternative is that mu Colorado minus mu Texas does not equal 0. Remember, we're looking for a difference in the average price. Step 3 is getting your test statistic. I can see from my output that it's negative 0.9018. And the p-value is right in the output too. It's 0.3761. All right, clearly that p-value is very big. 0.3761 is larger than our alpha level of 0.05. The p is not low, so the null does not go. Do not reject the null hypothesis. And now we can make our conclusion in terms of the alternative. This time, since we did not reject the null hypothesis, we do not have enough evidence for the alternative. So there is not significant evidence at the 5% level to conclude mean price for Zocor is different in Colorado and Texas. All right, so hopefully you're getting good at making those interpretations by this point. Now we're going to interpret the confidence interval. Now here it gets a little bit tricky, right? If all of the values for the possible values for the difference were positive, we would think that mu Colorado was bigger. And if all of them were negative, we'd think mu Texas was bigger. But we've got a problem. We have negatives and positives here. So what does that mean? If we think about putting these values on a real number line, for these possible values for the difference, we've got it going all the way up to 5.19 and all the way down to negative 13.24. Okay? So if the difference was 0, then mu c equals mu t. What if it was one of these positive values? If it was one of those positive values, then mu c is bigger. Mu Colorado is bigger than mu Texas, because if you subtract them and get a positive number, it means Colorado is bigger. However, if the real difference happens to be one of these negative numbers, then mu Texas might actually be bigger than mu Colorado, because if you take mu Colorado minus mu Texas and you get a negative number, it means mu for Texas is bigger. So if we were actually going to formally interpret this confidence interval, we would have to write 3 sentences. We would say, with 95% confidence, we are unsure if there is a difference in the mean price for Zocor in Colorado and Texas. If the mean price is higher for Colorado, it is by as much as $5.19. If the mean price is higher for Texas, what's the biggest difference in that direction? $13.24. It is by as much as $13.24. Make sure you don't put that negative sign on that number, because all that's telling you, that negative sign was telling you, was that Texas was bigger. By how much? Positive $13.24. All right, so I already knew after doing this hypothesis test that we were going to have a 0 in our confidence interval. How did I know that? Because my test for the difference resulted in a non-significant p-value, telling me there might be no difference at all. The null might actually be true. And we don't want to say that out loud, we just are kind of thinking it, right? Because we never claim that the null is true, but we're kind of thinking it. When we don't have enough evidence for the alternative, maybe so. So this 0 in the interval tells me that I'm going to have a high p-value when I test for the difference. That relationship is going to hold for our confidence intervals and hypothesis tests. And we'll use it a lot more when we do more confidence intervals, especially when we do like Tukey's in the ANOVA chapter. So it's something that we want to start paying attention to now. When 0 is in the confidence interval for the difference, the hypothesis test for the difference is going to fail to reject the null hypothesis, because the null hypothesized value is in the possible range of values for that difference. Okay, hopefully that was a good refresher of what you learned previously on looking at the difference in 2 population parameters.